In previous videos, I've looked at the definition of the derivative, done some different examples of that, and then also looked at basic derivative rules and a couple entry properties of derivatives. Those videos are linked in the description of this one. What I'd like to do in this video is to review a few of those rules real quickly and then expand on the properties that we have to the idea of how do you differentiate a multiplication of two functions, or how do you differentiate the quotient of two functions. Those two rules are called, first, the product rule when I'm differentiating a multiplication of two functions, and then the quotient rule when I'm differentiating a division of two functions. From the work with these extended properties that we have, we'll also be able to actually complete the list of how you differentiate the other four trigonometric functions, as well as some other things as well. Now, to get started, let's remind ourselves of what we had for our rules and also the very first properties. So first of all, the notation of the derivative of c with respect to x, I can do as like operator notation. And if you are taking the derivative with respect to x of a constant, you'll get the value 0. Next up, the derivative with respect to x of just x to the first, where these variables that you're differentiating with respect to and that you have in the expression that you're differentiating, that gives you a derivative of 1. The derivative with respect to x of x to the n power, where n is a rational number, is n times x to the n minus 1. The derivative with respect to x of e to the x is just e to the x. The derivative with respect to x of sine x is cosine x. And the derivative with respect to x of cosine x is negative sine x. Now make sure that if you don't already have those written down, you do write them down, because when I go to a new board with some other examples, I'll have erased those in order to make space to work out the new examples. So make sure to write those out. And then also for properties, we have the derivative with respect to x of a constant times a function in the variable that matches the letter that you're differentiating with respect to is just the constant times the derivative of the function. And then the derivative with respect to x of the addition or subtraction of two functions is just the derivative of the first function, and then plus or minus the derivative of the second function. And remember, another notation for derivative is to put a prime notation on the name of the function. But that's all we had before. But then what about when I have a multiplication of two functions and I want to find the derivative of that type of a function? Or if I have a function that's been created from the division of two functions, how do I handle those? Well, for some that we saw in the earlier video when we were just tied to these entry basic properties, we actually, if we could, multiplied out the multiplication of the two functions to get it to be term by term, and then we differentiated that. Or if it's a division and it was one where I had like a monomial denominator, I could break it up as the separate terms of the numerator over that monomial denominator, simplify each of those individual expressions, and again, differentiate them term by term. But there's a lot of times where I have products of two functions, or I have a division of two functions that can't be rewritten in a different way, or even those that can, maybe I want to handle them with the multiplication process. And so we want to find out what these derivatives are. Well, here's the thing, and why I needed to really wait until a whole different video before putting them in with the other ones that we had, is that when you're differentiating a product of two functions, it's not straight the product of the two derivatives. It's not a thing. So if you keep trying to do that, you'll keep getting them wrong. When you look at what you have to do when you're differentiating a multiplication of two functions, you have to take the first function times the derivative of the second function and add it to the derivative of the first function times the second function. That's the product rule. So it's important that you realize that there is more involved when you're looking at the derivative of a multiplication of two expressions in the variable that you're differentiating with respect to. Now, what about the quotient? Well, if you're differentiating with respect to the variable that the functions that are in a quotient are written in, then the way you differentiate that is the denominator function times the derivative of the numerator function minus the numerator function times the derivative of the denominator function all over the denominator function quantity squared. And if you look into like calculus textbooks and those sorts of things, you would see why they have to have this expression that they are equivalent to when you're taking the derivative. Back to the definition of derivatives and how to handle it so that limiting process is something that we can evaluate. That goes beyond the scope of this video. We're more about putting out what the product rule is and what the quotient rule is, and then looking at a lot of examples so that you can apply that to when you're asked to differentiate those types of functions. So again, make sure you take a moment to write this out. Be careful to have your good notation with it. So make sure that you put the derivative notation on that you're supposed to, but not on the ones that you're not supposed to. When you look at the derivative of a quotient, sometimes there's like this little sort of memory song or rhythm that you can get in your head to help you memorize the quotient rule, and think of your function that's in the numerator as the function that's high in the expression, and the function that's in the denominator be the one that is low. And then think of the phrase like D for derivative. Then it goes low D high minus high D low over low low. So if you kind of think of that low D high minus high D low over low low, that can kind of help you just keep that in your thoughts about what the quotient rule is. Next up, we're going to look at some examples. So here are our first two examples. In this one, I want to find the derivative with respect to x of x to the fifth times sine x. So here I have a multiplication of a variable expression times a variable expression, and the variable matches the variable that we're supposed to differentiate with respect to. So this is where we have a product of two variable expressions, so it can be looked at as coming from the product of two functions, and to differentiate it, I need to use the product rule. Now when I'm looking at this in terms of applying the product rule and the role everything plays in this, think of your x to the fifth as being your f of x and your sine x of being your g of x. So when I think about how to apply this, we're going to take our f of x function times the derivative of our g of x function plus the f prime of x, the derivative of our f of x function, times our g of x function. Now I'm going to write it in notation first, and then after that go back and look at what our derivatives would be. So it's our first function x to the fifth times the derivative with respect to x of our sine x. So I'm just setting it up to get started. Then plus, because that's the attachment between the two terms in the expansion of the product rule, and then our derivative of our first function, so the derivative with respect to x of x to the fifth, times our second function sine x. So that sets it up in notation. Next up, we're going to think about what those derivatives are. So this will be x to the fifth, and the derivative of sine x, if you look at what we wrote down earlier in the video at the start of it, the derivative of sine x is cosine x. and then plus. Now the derivative of x to the fifth, that is our letter base to our rational number exponent. So that is bring down the exponent of 5, keep the variable x, and subtract 1 from the exponent, make that a 4, and then times our sine x. So this gives me the derivative of that original function. And notice I don't have like terms here, so I can't combine them any better than having just that being our derivative. Let's look at the next one. So here's the derivative with respect to x of 7x to the fifth plus x cubed cosine x. So you want to try to think about overall what's happening with your expression that you're differentiating, and then what you have to apply at which stage of the process that you're going through. So the first thing I look at is that this has two different terms. Terms are split with pluses or minuses. So I have a term that's 7x to the fifth, and I have a term that's x cubed cosine x. Now, earlier we saw that the derivative of a sum or difference of two functions is just take the derivative of the first term and then use the correct sign that's attached to it and the derivative of the second term. So we're going to differentiate this with respect to x of that first term, 7x to the fifth, plus the derivative with respect to x of that second term, x cubed cosine x. Now, when I look at each of these individually, I have to pay attention to what's happening in them, to which property actually applies to that. So in this first term, I have a number times my function. And the derivative of a number multiplied to the function is just the number times the derivative of the function. So this will be 7 times, and my derivative of x to the fifth is 5x to the fourth. In the next term, this is a variable, a letter expression multiplied to a function of a letter. So this is the derivative with respect to x of this multiplication of variable times expression times action on a variable. So that's a product of two functions with the variable there. So I need to apply the product rule. So it'll be plus for this sign, and then we're going to go ahead and differentiate as we go. So it's the first function is your x to the third, and your second function in the product is your cosine of x. So it's the first expression, x to the third, times the derivative of the second one, and the derivative of cosine x is negative sine x. And then plus the derivative of the first function, so that's 3x squared, and then just times that second function, cosine x. So then when we go through and simplify this, I have 35x to the fourth, and positive x to the third times negative sine x is a negative x cubed sine x, and then plus my 3x squared cosine x. And this was operator notation. It's telling me to take the derivative of this in the question of it. So I'm just writing these stage by stage down alongside, or from one step to the next, until I finally got to the derivative of that expression. Examples, I'm actually giving a function by using function notation and then what the function rule is, and then asking you to find the derivative of that function with the notation. So here, instead of having the operator notation like the last one and then just working down from step to step below, I'm actually looking at this equation that's the original function, and I'm going to differentiate with notation on the left and then the application of the property on the right, or the rule on the right, to give my derivative. So I'm going to have to carry along a little different notation in this one than I did before. And you want to always make sure that you do that so that you are clear about what it is that you're finding, and when you look back at the question, what was the original function, what was the derivative of the function, and that sort of thing. So when I'm looking at finding the derivative, I see that this has a fraction bar that has my variable expressions in the top and variables in the bottom. So I need to use the quotient rule on this one. Now with my derivative now is what I'm looking at. The derivative is, and with the quotient rule, remember your top function is the high function and the bottom function is the low function. And we're going to go low d high minus high d low over low low. And I'm going to write out the notation for what we need to do in our differentiation and then take the derivative on the next phase. So when I'm looking at going through with this, my function in the denominator, the low, has more than one term. So when I start with it in this numerator to apply the quotient rule, I have to put parentheses around it. So this is going to be, my low is x to the fifth plus x, that's low, d high. So I'm just going to say I'm going to take the derivative with respect to x of cosine x, and we'll do it in the next phase. Then minus from the quotient rule, high d low. So this is going to be, the one in the numerator is just the cosine x, and that's going to be times the derivative of the function in the denominator, the derivative with respect to x of x to the fifth plus x. And then that's all over low low. So we have to actually grab that entire denominator and square it for our expression in our denominator. Now this next phase through, we're going to actually carry out the derivative. So my f prime of x equals, notice I want to keep track of what my function was and what my derivative is. So f prime of x is equal to, and I have that x to the fifth plus x. The derivative with respect to x is, of cosine x, is negative sine x, but I'm multiplying it. So I have to put it in parentheses, or else when I look at it, I'm going to confuse myself and think fraction instead of multiplication, but it's multiplication when you look at the quotient rule. And then minus cosine x times the derivative with respect to x of x to the fifth plus x. And this is two different terms, so I can take it as term by term derivative, but I need to put parentheses around it because it's multiplied to that cosine x. And I actually should be careful and put parentheses around that cosine x too, so I don't confuse what is the argument that cosine is acting on and what's not. So we're going to write then in the parentheses, the derivative with respect to x of x to the fifth is 5x to the fourth, plus the derivative with respect to x of x is 1. And then that's all over my x to the fifth plus x quantity squared. Notice there's not a derivative in the denominator, it's just that denominator squared. Okay? And then lastly, we're going to have our f prime of x is equal to, well, when I multiply this negative sine x through this binomial, I'll have negative x to the fifth sine x minus x sine x. And then think of multiplying negative cosine x through the binomial at the end here, and it's safer to write the variable expression in that multiplication prior to the trig function. So we're going to write minus 5x to the fourth cosine x and minus cosine x, and that's all over my x to the fifth plus x quantity squared. So that's what we have for the derivative of that quotient. Let me get this fraction bar in a little bit better for you. So that is our derivative of that quotient. let's try the next one. So here, f of x is equal to tan x. Well, tangent of x is not a trig function that we've already differentiated. We've differentiated sine x and we've differentiated cosine x. And right now, as far as the properties go, I have the properties of how to take the derivative of a term-by-term function and then of a product or of a quotient. But tangent x, and this is still the function, I'm just rewriting it so that I can get ready to differentiate it. Tangent x can actually be written as the quotient of two trig functions. Tangent of x is sine of x divided by cosine of x. And now I can differentiate it because I know what the derivative of sine x is, it's cosine x. I know what the derivative of cosine x is, it's negative sine x, and I know now how to differentiate a quotient. So I can actually find the derivative of tangent x through my trig identity that it's sine x over cosine x and applying my quotient rule. So my derivative f prime of x is low cosine x d high, so derivative with respect to x of sine x, minus high sine x d low, derivative with respect to x of cosine x, all over low, so all over cosine x quantity squared. Now, let's do the derivatives. So f prime of x is equal to, well, it's cosine x times the derivative with respect to x of sine x is cosine x. And then minus sine x times the derivative with respect to x of cosine x is negative sine x. All over cosine squared x. Remember that cosine x quantity squared is rewritten in a simplified or agreed upon way of writing it is cosine squared x. Now look what happens in the numerator. My f prime of x, in simplification, my numerator is cosine squared x and then negative sine x times negative sine x is positive sine squared x. And that's all over cosine squared x. Now here's where you want to remember your trig identities. In the 8 fundamental trig identities, and I've put the link to that video also in the description of this one, you'll see that cosine squared x plus sine squared x, or if you write it the other way, sine squared x plus cosine squared x, that is equal to 1 in our 8 fundamental trig identities. So I really have a numerator of 1 from a trig identity, and 1 over cosine squared x can be written as secant squared x. So we can now add to our list of derivatives that we have for our trig functions that the derivative with respect to x of tangent x is equal to secant squared x. Well, since we have 3 of the 6 trig functions derivatives already developed, so we know the derivative with respect to x of sine x is cosine x, the derivative with respect to x of cosine x is negative sine x, and we just found that the derivative with respect to x of tangent x is secant squared x. Let's see what the derivative of the remaining 3 trig functions gives us. So first is our f of x equal cotangent of x. Well, here I could actually go to the cotangent of x being the same as 1 over the tangent of x, or the same as cosine of x over sine x. In this simplification process, it will come up with the same derivative for cotangent of x, either way we go. Let's look at this as the function being the ratio of cosine of x over sine x. So basically I'm doing the video, so I get to pick which one we're going to do. Now, if I'm looking at that form, again, I'm just rewriting it from a trig identity. I haven't done any calculus yet. But now that I have it as a quotient of trig functions I know the derivative of, and I know how to differentiate a quotient, we're going to apply the quotient rule to this form of it and come up with our derivative. So then our derivative f prime of x, your high is the cosine x, your low is the sine x. So it's low sine x, d high, so derivative with respect to x of the cosine x, minus high cosine x, d low, so the derivative with respect to x of sine x, all over low low, so all over sine x squared. Now we'll go ahead and do the derivatives, and remember this notation was telling us and reminding us we still needed to differentiate it. We were just getting everything in place for the quotient rule. When we actually do the derivative, we'll not write that notation. So my f prime of x is equal to, well, sine x times, and the derivative of cosine x is negative sine x, minus cosine x times the derivative with respect to x of sine x is cosine x, and that's all over. Another way to write sine x quantity squared is sine squared x. Now simplifying this, I have a negative sine squared x minus cosine squared x all over my sine squared x. And then I have a common factor of negative 1 in the numerator that I can factor out. So factoring out that negative 1 will leave me a negative and then parentheses sine squared x plus cosine squared x. Now from what we did in the last example, in the last segment of this video, sine squared x plus cosine squared x is 1. So if I factor that negative out, I'll have negative 1 times 1, or a negative 1 in the numerator, and a sine squared x in the denominator. And then rewriting that with the reciprocal trig relationship, I get that f prime of x is equal to negative cosecant squared x. For our f of x is equal to cotangent of x. Let's look at the next one. F of x equals secant x. Well, here I really only have one way that I can rewrite this in terms of functions that I already know the derivative of, as well as what I can apply with my rules. So we're going to write this function secant x as its reciprocal function, 1 over cosine x. Once I've rewritten it that way, I'm going to look at this as the quotient rule. Later on, we're going to learn about what's called the chain rule, but that's in a later video. So here, I'm still kind of tied with the properties and the rules that I know, and so it's the quotient rule that we're going to look at. When I do that, the function in the numerator is 1, and the function in the denominator is cosine x. So now with our derivative, remember it's low, so cosine x, d high, so the derivative with respect to x of 1, minus high, 1, d low, the derivative with respect to x of my cosine x, all over low low, so all over cosine x quantity squared. So now I have for my derivative f prime of x, it's equal to, well, cosine x times the derivative with respect to x of 1. Well, 1 is a constant with respect to x. 1 is a constant. And so the derivative of a constant is 0. And then minus 1 times the derivative of cosine x, and the derivative of cosine x is negative sine x. All over cosine squared x. So in my numerator, cosine x times 0 is 0. And then negative 1 times negative sine x is a positive sine x. So my derivative f prime of x is equal to sine x over cosine squared x. And I'm actually going to write that as is equal to my sine x over cosine x times cosine x. And I'll tell you why in just a minute. Now what I need to do here is I want to write this in a form where I don't have a quotient in my formula for the derivative. So I'm going to think of that as 1 over cosine x times sine x over cosine x. And 1 over cosine x is secant x, and sine x over cosine x is tangent x. So for the function f of x is equal to secant x, its derivative is going to be equal to secant x tangent x. And I will write that up here. F of x is equal to cosecant of x. Well, the reciprocal of cosecant of x is sine x. So we're going to write this as f of x is equal to 1 over sine x. So now when I take the derivative, f prime of x, I want to think of this as a quotient. So my high function is 1 and the low function is sine x. I'm actually going to move that over just a little bit further. So now we're going to go low, sine x, d high, derivative with respect to x of 1, minus high, 1, d low, derivative with respect to x of sine x, all over low, low. So all over sine x squared. Working out the derivatives, f prime of x is equal to sine x times, well, the derivative with respect to x of 1 of that constant is 0. So I have sine x times 0 minus 1 times the derivative with respect to x of sine x is cosine x. All over sine squared x. So sine x times 0 is 0, and negative 1 times cosine x is a negative cosine x. So right now we have f prime of x is equal to negative cosine x. And again, I'm going to write my sine squared x as sine x times sine x. Now when we look at that as a product, I can think of that f prime of x as negative 1 over sine x times cosine of x over sine x. And that gives me, well, negative 1 over sine x is negative cosecant x, and cosine x over sine x is cotangent x. So my derivative for cosecant x is f prime of x is equal to negative cosecant x cotangent x. So there you have several examples of taking the derivative of a product of two functions or a quotient of two functions. I'll do another video with derivatives of the chain rule, but in there I will also embed some types of functions that are our older types that we've just done, so that you can get a good comparison of what rules you are to apply on which questions, and sometimes even within which portion of a question, because there's a lot of functions that have a combination of a lot of these things going on, and I just have to apply the appropriate property or rule at that part when I'm differentiating that piece of the function. So make sure that you keep practicing what these rules are and which ones are direct derivatives through the operating process in order to get the correct derivative for that type of operation between functions, so that you'll be successful in taking your derivatives.